There are ideas in science that are mathematically correct, yet so unsettling that even the people who discovered them quietly hoped nature would never allow them to exist. Black holes are one of those ideas. This is not a story about what black holes are or how they work. This is a story about doubt, about why some of the greatest physicists who ever lived struggled to accept that black holes could be real. If black holes were predicted so early in the history of physics, why did it take nearly a century for science to finally accept that they truly exist? Long before the term black hole ever existed, scientists were already flirting with the idea that gravity could trap light itself. In the late 18th century, John Michel in England and Pierre-Simon Laplace in France independently imagined what they called dark stars, objects so massive that once light left their surface, it would never return. Their reasoning was surprisingly simple and entirely logical within the physics of their time. Every object has an escape velocity, the minimum speed needed to break free from gravity. If that escape velocity became greater than the speed of light, then light itself would be unable to escape. The star would not be invisible because it was small or distant, but because gravity refused to let light go. On the surface, the idea sounds eerily close to what we now call a black hole. Yet, to 18th century physics, light was just another particle, and gravity was a force acting across empty space. Nothing about this picture suggested a fundamental breakdown of nature. It was a clever extrapolation, not a revolution. And that distinction matters, because although the logic was correct, the physical foundation beneath it was not. Without a new understanding of what gravity truly is, dark stars remained a thought experiment, not a real prediction about the universe. If the idea already existed in the 18th century, why didn't science recognize it as a black hole? The dark star idea made perfect sense inside Newtonian gravity. But that was also exactly why it could not become a real black hole. In Isaac Newton's universe, gravity is a force that reaches across space. Time ticks the same everywhere. And space itself is just an empty stage where things move. Nothing in that framework can turn no light escapes into a deep physical boundary. It can only turn it into a problem of speed. Here is the missing piece. In Newton's picture, light is not bound to the geometry of the universe, because there is no physical geometry to bind it to. You can treat light as particles and ask whether the force of gravity can slow them down. But you do not get a horizon, a one-way boundary that changes what it even means to move forward in time. A true black hole is not merely an object with strong gravity. It is a region where the causal structure of space-time rearranges itself, where escape stops being about engines and becomes about the rules of cause and effect. Newton's physics does not have that concept available. That is why the 18th century dark star remained an elegant extrapolation. It guessed the symptom, darkness, but it could not describe the mechanism, a change in space-time itself. To get from light, can't escape, to there is a horizon. Gravity had to stop being a force on a stage and start being a property of the stage. And that shift only arrives when Albert Einstein enters the story. So when space-time becomes a physical entity, what changes? When Albert Einstein introduced general relativity, gravity stopped being a force and became something far more radical. Mass and energy no longer pulled on objects across space. Instead, they shaped space and time themselves, bending the paths that everything must follow, including light. Motion was no longer about forces acting on objects, but about how objects move through a curved geometric reality. Almost immediately, the mathematics began to reveal consequences that were never part of Einstein's original intuition. Just 1 year after the theory was published, Karl Schwarzschild found an exact solution describing the space-time around a perfectly spherical, non-rotating mass. Buried inside that solution was a strange boundary, a radius beyond which the geometry itself tipped inward. Outside this radius, space-time behaved in familiar ways. Paths could bend, clocks could slow, but escape was still possible. Inside it, something fundamentally different happened. All possible paths, whether taken by matter or light, curved toward a single direction, not because of a pulling force, but because the geometry itself no longer allowed any route outward. In purely mathematical terms, space-time had created a one-way region. This was the true birth of the black hole concept, even though no one called it that yet. For the first time, darkness was not explained by insufficient speed, but by the structure of space-time itself. Gravity had crossed a conceptual threshold. It was no longer just strong. It had become absolute. And yet, despite what the equations allowed, Einstein himself remained deeply uncomfortable. If mathematics permitted such a region, why did he still believe nature would never actually create it? The discomfort was not philosophical hand-waving. It was rooted in the very heart of the theory Einstein had created, deep inside the region allowed by the equations. Gravity did not merely become strong, it became infinite. Density, curvature, and tidal forces all diverged without bound. This point, later called a singularity, was not just extreme. It was a place where the theory stopped making predictions altogether. For Einstein, this was a warning sign. A good physical theory might describe strange realities, but it should never destroy its own ability to speak coherently about nature. A singularity looked less like a real object and more like a signal that the mathematics had been pushed beyond its domain of validity. The strangeness did not stop there. From the perspective of a distant observer, anything falling toward this region appeared to slow down endlessly. Clocks near the boundary ticked ever more slowly. Light grew dimmer and redder, and the moment of crossing seemed to be postponed forever. To the outside world, time itself appeared to freeze at the edge. Even more troubling was what this implied for cause and effect. If signals could never return, if time itself behaved differently depending on who was watching, then the familiar structure of causality began to feel fragile. For physicists like Einstein and Arthur Eddington, these were not deep truths about nature. They were absurdities. Signs that something had gone wrong long before reality itself was reached. The hope was simple and deeply human. Somewhere, some physical process would intervene. Stars would stop collapsing. Nature would enforce a limit. The equations might allow black holes, but the universe itself surely would not. But does nature care about what we find absurd? Nature did not step in to save our intuitions. In 1939, J. Robert Oppenheimer and Hartland Snyder followed the equations to their logical conclusion and found something unsettling. For a sufficiently massive star, once nuclear fuel is exhausted, there is no known force in general relativity capable of halting the collapse. The contraction does not slow, hesitate, or reverse. It continues all the way inward. This was not a speculative argument. It was a clean calculation carried out within Einstein's own theory. If the equations were taken seriously, Gravitational collapse was not an exotic possibility. It was an unavoidable outcome for massive stars. The hope that nature would impose a hidden stop simply was not supported by the math. Still, some physicists wondered whether this result depended too heavily on idealized assumptions. That doubt lasted until the 1960s, when Roger Penrose changed the conversation entirely. Using global geometric arguments rather than special symmetry, he proved that singularities are not fragile accidents. Under broad and realistic conditions, general relativity itself predicts that space-time must tear into a singularity. With that result, black holes crossed a line. They were no longer mathematical curiosities hiding in the margins of equations. They became robust predictions of a theory that had already passed every experimental test thrown at it. From that moment on, the question was no longer whether black holes were allowed. It was whether the universe had already made them. And when black holes moved from theory into reality, something deeper began to collapse along with our certainty. What exactly starts to break down when black holes truly exist? Few ideas in physics feel as counterintuitive as the event horizon. To a distant observer watching from far away, an object falling toward a black hole never seems to fully cross it. As the object approaches the boundary, its clocks appear to slow down. Its signals stretch and fade, and each moment takes longer to reach the outside world. From this perspective, time itself seems to freeze at the edge. This picture has fueled countless misconceptions. It feels as if the black hole is swallowing objects in slow motion, trapping them on its surface forever. But this freezing is not a physical barrier. It is a consequence of how gravity distorts time for observers in different locations. The mistake is assuming that this single viewpoint tells the whole story. For the infalling observer, the experience is entirely different. Their own clocks tick normally. Nothing special happens at the horizon itself. There is no sudden wall, no dramatic flash, no moment where time stops. The crossing occurs in a finite amount of personal time. Just as predicted by general relativity, what looks frozen from afar is perfectly ordinary from within. These two descriptions do not contradict each other. They reflect the fact that time is not universal. In a curved space-time, different observers slice reality in different ways, and both slices are equally valid. The event horizon is not a place where physics breaks. It is a place where our everyday intuitions about time and motion stop working. If the event horizon itself is not the real problem, then where does the true trouble begin? By the time we reach the singularity, even the idea of inside begins to lose its meaning. This becomes clear when physicists represent black holes using Penrose diagrams, where the entire infinite space-time is compressed into a finite picture without losing its causal structure. In these diagrams, the singularity does not appear as a place you travel to. It appears as a moment in time. For anything that has crossed the event horizon, the future does not lead outward. It leads inevitably toward the singularity. In the same way that tomorrow inevitably follows today, inside a black hole, reaching the singularity is not a choice or a direction in space. It is as unavoidable as the passage of time itself. Asking what lies beyond it is like asking what comes after the end of time. This is where general relativity quietly collapses under its own weight. The theory insists that space-time must end, yet offers no rules for what that ending means. Curvature becomes infinite. Trajectories terminate. And the mathematical language that once described gravity with elegance falls silent. General relativity does not merely predict its own limits here, it runs directly into them. This is why singularities are not just extreme objects. They are signals. They tell us that our best description of gravity is incomplete, that somewhere beyond this boundary, a deeper framework must take over. The singularity is not the final mystery. It is the signpost pointing toward one. But the greatest paradox does not actually live at the singularity. Just when black holes seem to be safely locked behind their event horizons, Stephen Hawking introduced an idea that changed everything. By combining quantum mechanics with curved spacetime, he showed that black holes are not perfectly black. Quantum fluctuations near the horizon allow particles to escape, making the black hole slowly lose mass. This process became known as Hawking radiation. This result carried a shocking implication. If black holes radiate, they must have a temperature. If they have a temperature, they must evolve. And if they evolve, they must eventually die, given enough time. Even the most massive black hole will evaporate completely, leaving nothing behind but empty space. At first glance, this seemed like progress. A universe without eternal prisons felt more reasonable. But hidden inside this picture was a far deeper problem. Everything that falls into a black hole carries information. Not vague information, but precise quantum details about the state of matter and energy. If the black hole evaporates and disappears, what happens to that information? According to quantum mechanics, information cannot be destroyed. The equations that govern particles and fields are reversible. Given complete knowledge of the present, the past is, in principle, recoverable. Hawking's calculation appeared to break this rule. The radiation coming out seemed completely random, carrying no trace of what had fallen in. Information, it seemed, was being erased from the universe. This was not a minor inconsistency. It was a direct collision between the two pillars of modern physics. General relativity described black holes. Quantum mechanics demanded that information be preserved. They could not both be right in the same way. Something fundamental had to give. If black holes can truly erase information, can we still trust the laws of physics themselves? By the end of this journey, a subtle shift takes place. The problem no longer looks like a black hole behaving strangely. It looks like our descriptions of nature refusing to fit together. Black holes are not breaking the laws of physics. They are exposing a crack between them. General relativity speaks the language of smooth geometry, continuous space-time, and deterministic evolution. Quantum mechanics speaks a very different language, one of probabilities, discrete states, and information. Each theory works astonishingly well within its own domain. But black holes force both languages to describe the same object at the same time. When we do that, the contradictions surface. Information cannot be lost. Yet black holes seem to erase it. Space-time must remain smooth. Yet singularities tear it apart. These are not failures of black holes. They are failures of a patchwork description of reality that was never meant to be complete. In that sense, black holes are not cosmic monsters. They are messengers. They mark the places where our best theories stop talking to each other, and where a deeper, unified description of nature is being demanded. Perhaps black holes do not destroy physics after all. Perhaps they simply reveal the limits of how we currently understand the universe. In the end, Einstein did not doubt black holes because the mathematics was wrong. He doubted them because he understood, better than anyone, The philosophical price of accepting what the equations were saying. To accept black holes was to accept singularities, endings of time, and a universe where our most trusted descriptions fall silent. Black holes do exist. Observations have confirmed them beyond reasonable doubt. But their existence does not bring closure. It brings a responsibility. They force science to admit that some structures can be mathematically consistent, physically real, and yet still fundamentally misunderstood. Perhaps that is the deeper lesson. The universe does not promise comfort. It does not guarantee that understanding will come easily, or at all. Sometimes, it only offers us hints, boundaries, and questions that point towards something greater than our current theories can reach. Black holes may not destroy physics. They may simply remind us how much remains unknown.